A hallmark of most geometry classes, as well as any higher level math at the college level that is beyond calculus, is the idea of proof. And this video is going to take you through the basics of what a geometric proof is, as well as guide you through two proofs so you can see the way that we organize our thoughts when we actually go through these things called geometric proofs. But before we can talk about how to complete proofs, we have to talk about what proofs are. And at its core, a proof is just a series of logical steps that show that a statement must be true based on information that we know. Now, this is something that you're actually kind of familiar with already, though not necessarily in a mathematical context. In a mathematical context, the series of steps that you follow to solve a complex equation is in some ways an algebraic proof, because you go step by step to show that the value of x or y or whatever variable it happens to be must be some particular number. On the other hand, if you've ever written a paper in an English class or something like that, where you have a statement at the beginning of the paper and you lay out a series of logical arguments to show that your statement is true, you have engaged in a type of proof process. Mathematically, it means that we need to give a reason why each step that we take is true. Another type of conversation that is related to proof and has a series of similar thoughts is that if you've ever been in a conversation or an argument with someone about a favorite band or favorite song or favorite ice cream flavor or favorite food or something like that, and you're trying to convince the other that one is better or trying to convince someone to make a decision, then you may have gone through a series of statements that are designed to build logically on each other to convince the other person of something. All of that falls under the thought processes that we use when we're actually putting together a proof. Mathematically, though, there's a little bit more rigor to it in some ways, and we need to give a reason why each step that we take is true. In geometry, we often format proofs in something called a two-column proof. And before we talk about what exactly a two-column proof is, let's look at an example of it, and the idea will become, if not obvious, then more evident to you. So an example of a geometric proof could be in a diagram like this. We know that VW and XY intersect each other at point Z. If we know that VZ and XZ are congruent, and we know that YZ and WZ are congruent, we would be asked to prove that VW is congruent to XY. Now take a second to look at this. See if you can convince yourself informally that this must be true based on what we know. Then we will go through and see a few different ideas about the proof and actually construct the first proof together. So one of the key things to recognize in the diagram is that each of our segments has this little blue mark on it that we can call a tick or a hash mark or something like that. And whenever two segments are marked with the same number of ticks or hash marks, it means that the segments are congruent. So here, the fact that VZ and XZ both have a single blue mark means that they're congruent. And the fact that YZ and WZ both have double blue marks means that they are congruent, but VZ and ZW are not necessarily congruent to each other. So as we're thinking about how to set up this proof, it should be, or probably is, relatively obvious or straightforward to think that, well, if we have two things that are the same, and we add each of them to one of two other things that are also the same, then the two resulting sums, or the two resulting lengths, should also be the same. And a lot of what we're going to do with proof is going to be relatively intuitive, that based on what we know, what we want to prove should happen. So now let's go through an example of a two-column proof to show how we go through this process. A two-column proof is called a two-column proof because we create two columns. The left-hand column is a bunch of statements, and the right-hand column is the reason why we know that. And the first step of every proof is to rewrite the given, because the given is what we know. It's the things that we are assuming to be true. So we know that VZ is the same as XZ, and we know that YZ is the same as WZ. Why? Because those are given. Notice that I didn't use the congruent signs or the line segment marks because VZ and XZ without those marks are the length of segments VZ and XZ. So now what we want is to prove that VW and XY are the same. One of the ways we can do that, and one of the things we should always be thinking about, is how can we create VW? Well, what we know is that VW is made of VZ and ZW, and we know that XY is made of XZ and ZY. So the next thing that we're going to look at is how can we get xz and zy together, and how can we put vz and zw together? Well, it turns out if we add the two equations that we have here in a particular way, so that vz gets added to wz and xz gets added to yz, then we have those two segments that we're interested in. And because we can add equal values to both sides of an equation and produce an equivalent equation, we can do that here. We can say that vz can be added to wz, and xz can be added to yz and be the same, because this is what we saw in the equality video. This is the addition property of equality. Take our original equation, vz is equal to xz, add congruent values to each side, that wz is added to y and is equal to yz, and then we have two equivalent equations, and our equation does not change. So now vz plus wz is in fact vw, and xz plus yz is in fact xy, because of the segment addition postulate. We can add the lengths of segments, or two segments together, and we get a new segment. And that is exactly what we wanted to prove. So here, it may be obvious that add two congruent things to two other congruent things and the resulting sums are congruent, but mathematically, we need to state the given. We need to add the two things together in a particular way, using the addition property of equality, and then simplify vz plus wz equals vw and xz plus yz equals xy using segment addition. Let's take a look at one more proof, and then you're going to be asked to download a skills practice where you're going to go through some guided proofs where I give you either a statement or a reason, and you provide the other. Here, let's look at some angles. We know that the measure of angle AOC is the same as the measure of angle BOD, and we want to prove that angle 1 is congruent to angle 3. Well, like we saw in the last problem, we have some marks on this diagram. And what's true about angles is that whenever two angles are marked with the same type of arc, that means that the angles are congruent. So the orange arc that moves from the ray OA to the ray OC is the same as the orange mark. It doesn't have to be the same size, just has to be the same type of arc, from OB to OD, which means that angle AOC and angle BOD are congruent. The same way that we saw in the segment addition proof, in this proof involving angles and angle addition, we're going to take each step one by one and show why each of the steps must be true. So again, we set up our two-column proof with statements on the left and reasons on the right, and we always start with the given, that the measure of angle AOC is equal to the measure of angle BOD, because that is given. So now in this case, we can look at angle AOC and say, well, angle AOC is made up of angle 1 and angle 2. So that means that angle 1 plus angle 2, actually, let's add one more step here. If the measures of the two angles are equal, that means that angle AOC is congruent to angle BOD, so we can get straight to the angles and not to the measures, and that's by the definition of congruence. It's a step that we don't necessarily need to take, but one that makes the proof a little bit cleaner. So now angle AOC is made up of angle 1 plus angle 2, because those are the two angles here. And angle BOD is made up of angle 2 plus angle 3. Those are these two angles over here. And why is that? That is because of angle addition. That's what we saw in the angle addition postulate a little while ago. Now that we have angle 1 plus angle 2 is congruent to angle 2 plus angle 3, we can subtract angle 2 from both sides to get angle 1 is congruent to angle 3 by the subtraction property of congruence. So That is an introduction to the way that proof is constructed. We could have left this as measure of angle AOC equals measure of angle BOD, said measure of angle 1 plus measure of angle 2 equals measure of angle 2 plus measure of angle 3, subtracted the measure of angle 2, and then said angle 1 is congruent to angle 3. So what we saw here, two proofs, one involving angles, one involving segments. In both cases, you start with a given, you manipulate around using things that we know are true, like the addition and subtraction property, the fact that we can add and subtract angles and segments, and then eventually get to what we want, giving reasons for the truth of each step along the way. Like I said, the practice that you're going to be doing for this introduction to proofs is going to be a skills practice problem set that has 4 proofs for you to complete. But for these proofs, I'm going to give you either the statement or the reason for each step, and your goal will be to provide the other one. As we go throughout the course, you will become more and more comfortable with these types of proofs, and you will be able to do more and more complex proofs. If it seems a little bit confusing right now, that is totally okay. You have thought in this way before, but you have never been asked necessarily to write it down in this particular format. But once you get used to proofs, the methodology behind it starts to become a little bit more second nature.